Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick. In this episode, we sit down with Pratyush from UC Berkeley to talk about Zexe, which is a paper for a new type of private smart contract blockchain.
Before we start, we want to say thank you to this week's sponsor, Aragon One. If you love working with talented designers building smart user interfaces, or if you're really excited about making DAOs easy and accessible to create and manage, then you should check out Aragon One's available job openings. The project is currently hiring a front-end engineer to help build the platform for modern organizations. For more about the front-end engineering role or other available jobs, check out aragon.one/jobs. That's aragon.one/jobs. So thank you again, Aragon One. Now here is our interview with Pratyush.
Today we're sitting down with Pratyush to talk about Zexe, and it's a project I'm very excited about. We've kind of teased it in episodes past, and let's finally dig into what it is. And we're also here with Anna, as usual.
Hello.
Welcome to the show.
Oh, hi, everyone. Thanks for having me on the show. Yeah, it's a pleasure to be here. I'm excited to talk about Zexe.
So first of all, let's talk a little bit about you and where you're coming from. What's your background and how did you get involved with this?
I do cryptography as a part of my PhD. So I'm a PhD student at UC Berkeley. I just finished my third year. So my background is really, I work on zero knowledge proofs and applications thereof. So I started off my PhD with working on this project called Decentralized Anonymous Micropayments. And that was in some sense the precursor to Zexe. And what that project did was basically trying to take a Zcash-like protocol and give it some flavor of micropayments. As micropayments are basically very tiny payments, and how to do those efficiently without suffering from large transaction fees. So anyway, that project had some notion of computation in there somewhere. And what we did with Zexe after that was to try to extract that and formalize it and actually have an implementation. And so that's where I got into Zexe. Before that, yes, in general, I was very interested in cryptography, which is why I started my PhD in there. And yeah, here I am now.
What is it about this stuff that actually gets you excited? Is it math? Is it cutting? Like, what's the thing that attracted you to this?
Attracted me to cryptography. I think just the concepts in crypto are pretty mind-blowing. Like zero knowledge proofs. Like here's this concept where I can prove something to somebody and they'll be convinced, but they won't learn anything other than the fact that what I'm claiming is true. That is a pretty insane topic by itself. There's also this notion of, multi-party computation, where a bunch of people can come together and compute. Each has some private input. And at the end, all of them learn the output of the computation, but they don't learn any of the other person's input. So the only thing we learn is the output. And so I was being introduced to these concepts as an undergrad. I was also at Berkeley. It was just mind-blowing that such thing would be possible. What drew me specifically to, I guess I work on more of the applied side of cryptography, so trying to take this stuff and making systems that people could potentially use out of it. So yeah, what drew me to that is, a lot of results in cryptography have been very, in some sense, theoretical. I mean, there's a promise of taking it to practice, but people have not been really able to. Maybe that's because people in the real world don't care about privacy, or I don't know. So what I was interested in was trying to take some of this stuff and actually make it practical and usable for people.
In the past, there have been cryptographic ideas that have been implemented. It just took a very long time. Do you think in the space that you're working in right now, it's just faster?
So for a long time, I think in cryptography, like what is used in industry or like in the real world, was really the very basics of cryptography, like signatures or encryption. And these things we've known how to, at least theoretically do for ages. But a lot of this interesting stuff like zero knowledge proofs or MPC, we've also known how to do for since the 80s, mid 80s. That's when the first theoretical results about these came about. But there hasn't been a similar, infiltration into the real world use cases. I think recently, at least for zero knowledge stuff, maybe in general, privacy has become more important as you get a lot of, this big data stuff and people becoming more concerned about how the data is used and spread around. So, for example, in the blockchain world, because everything otherwise is public, that's why zero knowledge proofs have seen like a lot of interest has been generated in these proofs, also for scalability. And I think now, for example, in other parts of industries also, this multi-party computation is becoming interesting. So yeah, I think maybe now is perhaps the ideal time to be getting into just at the transition period to be like working on this stuff. So it's definitely exciting for me. Like when I started, there was no prospect of going to industry and working on all this cool crypto. But now there's openings.
Do you think the world has been better educated about a lot of this stuff? Do you feel like outside of academia, there's more and more interest?
I think definitely within the blockchain space, there is a lot of awareness, much more than expected. I was at the ZK proof workshop earlier this year, a couple of months ago, and I did not expect there to be that many people interested in zero knowledge proofs. So that was certainly a very pleasant surprise. I think, so maybe in the blockchain space, there's quite a bit of awareness. I think outside of that, still in like the rest of industry, there's a lot of room for people to become aware of it. And that's partially on, probably mostly on cryptographers as well, because sometimes we tend to be like siloed up and not
ready to maybe dumb it down a little.
But actually, part of it is like better education and simplifying how we explain stuff. Part of it is actually just trying to go out and look for use cases and try to engage with people in industry. That can be difficult because like conflicting interests all over the place. And
it seems like that has been a lot of the path of awareness and adoption in the blockchain space. Is like Zcash came out and did it and showed a successful use case, and then it's sort of easier to understand the context and how to use it and sort of where it fits in. And maybe other industries just need their use cases to look to and sort of get the inspiration to then dig in.
You sort of mentioned this other project that you were involved in that led to the Zexe project. Was there anything else that you were working on in your studies that kind of fed into this?
So directly related to Zexe, not quite. I have a couple of other projects ongoing and done in the past that are in like other areas of applied crypto. Like one is in some sort of encrypted search where, let's say that I upload my, files to some cloud server. How can I retrieve the files without telling the server, okay, this is my file, telling what the contents of the files are? So that's one project. There's making use of like hardware enclaves and SGX and stuff. So not like directly related to Zexe. And I have some ongoing work in some sort of private machine learning sort of area as well. But yeah, so related to Zexe, I guess like just working on zero knowledge proofs. And yeah, this decentralized anonymous micropayments was really like the core stuff in the pipeline up to Zexe.
Now would be a really good time to talk about Zexe or Zexe, if anyone's curious how that looks.
Yeah, I've heard a lot of discussion around whether or not the name is a good choice. But
it sticks.
It's Zexe, and I suppose it stands for like zero knowledge execution or something like that.
Yeah, that's the aim that we're going for. It helps that it's a provocative name, so certainly sticks in the memory.
We actually have had, I remember when we had Benedict on talking about bulletproofs, we actually had a little section where we talked about how that name came to be. Where did this name come to be?
So we had a lot of iterations on the names. I don't remember all the candidates. At some point we had something like Zeke, Zeke, and we were like, okay, that's an okay name, but like, who is Zeke?
Zeke is a character from a TV show in the 90s. It's a generic character name, Zeke. Maybe a boy band. Yeah.
That's possibly, I was too young to get that reference. But then we were like, okay, so zero knowledge is the K, I guess, but we have this execution thingy. Why are we like limiting that to just one letter? And so then we were like, okay, zero knowledge execution. How do we, shorten that? I mean, so like the core primitive in Zexe, we call it Decentralized Private Computation, or DPC is like the name for that in the paper. We were like, okay, should we put that as the name of the thing, of the paper as well? And we were like, no, that might confuse people because there's this other area of crypto called MPC, which is multi-party computation. Like, okay, Zexe seems nice, and it's certainly interesting to say the least. And
did you make it an acronym? Does it stand for
Yeah,
something larger, or is
zero knowledge execution?
It is zero knowledge execution.
Yeah.
Got it.
So what is Zexe?
It's a system for doing some sort of any arbitrary private computation on some decentralized ledger. So, if you take something like Ethereum or I don't know any of these smart contract systems, how they work is that when I want to execute a smart contract, I publish a transaction, and then everybody, all the miners in the system, or any full node who wants to verify my transaction, has to re-execute the computation inside the transaction, right? And this has problems in terms of privacy and scalability. In terms of privacy, like you have to execute the program, you need to know what data goes in, who called the program. And in terms of scalability, re-executing computation can be expensive. So what we try to do in Zexe is try to address both of these problems. So from a privacy perspective, what we try to do is support general computation. So you can perform, like Ethereum, any arbitrary computation, while hiding what program is executed, what data is input to the program, as well as who invoked the program. So all that information should remain hidden. And also we wanted the cost of the system to not really scale with the computation that you're doing. So even if I do a very heavy computation, the people who are verifying my computation on the ledger, which they will be doing many years in the future, I want to minimize the cost of them. So I want that to be independent, that cost of verification to be independent of the cost of my computation that I did offline. And so, yeah, Zexe's system just tries to achieve both of these goals by relying technically on snarks.
When I first heard of Zexe, I wasn't clear if it was something that would sit on top of a smart contract platform or if it itself was that platform. And I wonder, where do you see it?
So how we, while designing system, envisioned Zexe to be deployed, we haven't deployed it yet, but how we thought it would be deployed is you have some arbitrary, consensus mechanism underneath that provides you with some sort of, block chaining mechanism. And that's all you need. And then Zexe implements the computation aspect of it, the privacy aspect of everything. So it really sits as its own blockchain separately. You could potentially try to deploy it as a smart contract within the Ethereum ecosystem, but that would require, lots of additional engineering considerations, and then the privacy guarantees and scalability guarantees, all that would change as well. So we really thought, in speaking in terms of like this layer parlance, sitting at the L1 level and not at like L2 scaling solution or privacy solution.
When you talk about these arbitrary consensus mechanisms or setups, like what would that be?
So like proof of work or proof of stake or
a permissioned system.
Or permission.
Okay.
It really, you could be running on some single person's computer somewhere in the world, as long as it provides some sort of like blockchain that you can verify that, this block came after this block. That's all you really need.
So let's dig into this a little bit more. Imagine it is a blockchain. You have transactions coming in. You have transactions piling up and blocks being produced. Are contracts deployed to the chain publicly, or are those private as well?
So unlike Ethereum, Zexe doesn't work in sort of this account-based model. It works in more of a UTXO-based model. So for people to be able to use a smart contract, they need to agree like what the code of the contract is. So in that sense, the code of the contract is publicly available at some point, perhaps only to the people who care about the contract executing. Maybe everybody else doesn't care, so they don't know it. But going back, so because it works in this UTXO model, roughly how you can think of it is that if I have a coin that's associated with, in Zexe, it's associated with a so-called birth and death scripts or predicates. And the idea is that when I consume the coin, when I spend it, that corresponding predicate must be executed, so must be satisfied. So you think in like the Bitcoin world, you have these Bitcoin scripts, right? So if you have like a pay to script hash sort of address, then when I want to consume or spend a coin which is living at this address, I have to satisfy the corresponding Bitcoin script. So similarly in Zexe, instead of the script, we have this death predicate. And when I want to spend the coin, I have to satisfy the death predicate. So the code for the coin, for the contract really lives inside each coin in some sense. It's associated with each coin.
I always think of smart contracts as being like deployed to something. And what you described is it sort of like lives somewhere, but not.
So the idea is roughly, so when I create a coin, right, I associate that coin with some sort of code. And when I want to consume that coin, that code must be executed and the checks inside that code must be satisfied. So really, the code is only executed when the coin is spent. So it's like when you spend the coin, you're invoking the contract in some sense. If you could implement, I don't know, something like Zero Cash or Zcash inside Zexe by having your code be, it checks that the value of the input coins is equal to the value of the output coins. And now when I spend a coin, this code is executed, so it checks that the input coins are equal to the output coins in terms of value.
This in general is, a quite different computation model to something like Ethereum, like you said, where, people familiar with Bitcoin and Bitcoin script probably understand this and just sort of it's intuitive and like how Bitcoin script executes. In Ethereum, though, the model is you deploy this contract and then you can, send a transaction to this contract with zero balance and you just pay for the gas to execute whatever it is, and you have some output of that contract, or it's to store some state or whatever it may be. You don't really have that here. You kind of, with your transaction, you deploy a piece of code, and then whoever is the other party in this computation executes that code to consume the coin, and then I guess it's gone.
Yeah, it could be self-propagating. You could have the predicate say, okay, the next output coins must also have this whatever X predicate or X code inside them. So yeah, it's a very different model from Ethereum, so that you're not really, telling the contract, please run yourself. You're actually executing it within the transaction, and then you could plausibly have a coin which is only whose only purpose is to execute the code. But the point is that now when I spend that code coin or whatever, then that coin is consumed. And it can be self-propagating. So it can say, okay, once I'm consumed, please in the output make sure that there's another coin of my same code, whatever. And then this keeps on going. But it's not like this permanent account that lives in the Ethereum world. Here you can have the same sort of permanence of the code, but it has to be some sense self-propagating. So we've actually had, this is not a uncommon thing to have. We had lots of troubles actually figuring out how do you program stuff in this model? Is it useful for anything? And I know so far we found that a lot of the useful applications are really in this sort of financial sort of world where we are really interacting with tokens. And there, this notion of self-propagation makes sense. You can say, okay, this coin, it can only be spent if the other coin is of type B or something in the transaction. So then your predicate really is reasoning about local information, right? So then it makes sense. Reasoning about global information requires really sort of free shifting your understanding of how to write the code. And it might not be, I don't know, it's possible that we can't think of applications where it's entirely clear how to make use of this model and how to write efficient code that propagates.
There's obviously some big differences and trade-offs in how these different models work. You're not going to deploy a huge contract with this either, because you're limited in transaction space, and you're not going to run CryptoKitties in this way, because it's sort of you need to breed kitties then and store them somewhere and self-propagate this thing and redeploy it every transaction. It's not suitable. But clearly there are some other things where it is more suitable. And I'm curious, how does the programming language, whatever the script or the assembly or whatever that is, compare to something like the EVM or something like Bitcoin script?
So currently Zexe is at a pretty, a very, very beta state. So we haven't in the implementation, for example, decided on what the official programming language or scripting language for this would be. In the implementation, we just write arithmetic circuits and our R1CS constraints systems and put those inside a snark. So we don't have some sort of Solidity or Bitcoin script type language or ZKVM type language. It's entirely plausible that one could implement these on top of our protocol, because snarks can do any computation, right? But yeah, so we don't have, as I said, it's a very beta state, so we don't have anything like a standard library for developers to use, or even a syntax for what a language would look like.
But would you see that as a future step if somebody would like to run with this?
For any sort of plausible usability or deployment, you would have to standardize on some sort of efficiently executable scripting language that is sufficiently high level that people could use without shooting themselves in the foot. Because programming snarks directly is a pain. I have enough experience with that.
So, I mean, in essence, this predicate, the script that you deploy is a snark. And then the person who executes this, has their input parameters, creates a proof that they've run this execution correctly in this snark. And then in what they send back to the chain, I guess, is this proof. And then it can be verified.
Yeah, almost exactly. So we have a little bit of an extra step. Basically, as you said, the person who's creating the transaction, they execute the computation, produce a snark for it. And this snark is basically a test that the computation was done correctly. But this doesn't quite get you to our goal of like super strong privacy, where we want to also hide which function executed. Because for modern snarks, roughly, if I want to verify the snark, I need to know like what function the snark is for. So if the blockchain wants to verify the snark, it has to know which function the snark is being produced for. And this compromises our goal of so-called function privacy. So what we do is do another level of so-called recursion. So we use a snark to verify that these per application snarks are themselves correct. And because this snark, this big snark, is zero knowledge, we hide all information about the per application snarks. But in the end, what the chain is verifying is this big snark, which attests to the correctness of the predicate proofs.
Who runs the proof for the big snark?
It's the person creating the transaction. So when they create the transaction, they have to create this big proof, verifying proof.
This is only one level of recursion.
Yeah. So basically, my advisor Ale and a bunch of his co-authors back in 2014 or so, they had this very nice paper on so-called recursive snarks. And the idea there is that what you want to be able to do is you want to have a bunch of snarks verifying snarks, verifying snarks, verifying snarks. You have this endless chain of so-called snark verification. This is based on the cycle of elliptic curves. There's some number theory stuff that's probably not necessary. But anyway, this is also something that Coda is using. So this sort of recursive composition idea.
But they're doing it like quite deep.
Yeah, they go like basically infinitely. That's their goal. But the point is that this is maybe necessary for something like blockchain scalability, where you keep getting more and more blocks being produced. So you have to keep verifying the past state. But in our case, we don't really have that sort of concern because we only need to verify one level of proofs, the predicate proofs. We don't need to verify, like those proofs don't need to verify other proofs and so on and so forth. So when the person who's creating the transaction, they just make this 1 mega proof that verifies these small proofs, and that's it. And they publish this to the ledger. And verifying this mega proof is still constant time.
The bigger proof, you said, verifies many smaller proofs. What are the many smaller ones? If I'm just, executing one predicate or like one transaction, one into this one? And then if I want to execute multiple transactions at the same time, I can verify all of them, or what? So
what I mean by multiple proofs is that within one transaction, you're going to have like probably at least one or more input coins and one more output coins, right? So, what we have in the implementation is we fix it to be 2 in and 2 out. So each of these 2 inputs and 2 output coins, they have associated predicates. So the 2 inputs have so-called what we call death predicates or death scripts, and the outputs have so-called birth predicates that dictate conditions on their birth. And now this mega proof has to verify the correctness proofs for each of these 4 each of these predicates. So you have 2 death predicate proofs and 2 birth predicate proofs, and the mega proof verifies all of these 4.
I see. That makes sense.
Why would you have two coins? Is this sort of like if you're doing a trade? Like, are they?
It's just a Bitcoin detail.
Oh, is it?
No, the idea is that, at the very minimum, you need, I don't know, what I want to do in a trade is, for example, if I don't have enough money in one coin, I need to be able to combine coins, right? So I need to have at least 2 coins so I can combine them. And then if I want to have some change from the transaction, right? I want to send, if I have, 15 coins coming in, but I only want to send 10 coins to the vendor. I want to have a change address. So then that's why I need the 2 out as well. So 2 in 2 out is really the minimum that you would want for any sort of functionality.
Yeah. That's the standard Bitcoin UTXO model thing. If you had 1 in, 1 out, you could only pay if you had the exact amount to pay, and you could never get change on anything.
Got it. Is there any case where you'd have more than 2?
Well, you could have, if you wanted to reason about lots of different... So in Zexe is not just for payments, it's supposed to be for like arbitrary computations, right? So instead of having just coin value inside a coin, what we have in Zexe are so-called data records, and they store arbitrary pieces of data. So now if you want a transaction to reason about lots of different pieces of data coming from different sources, then you might want more than 2 in, 2 out. You could have, 3 in, 5 out, 5 in, 10 out, 10 in, 5 out, whatever.
So is this already defined in this sort of arbitrary fashion that you could tack on as many as you want? Or is that theoretical you could? So
the code base that we have, it's entirely generic in terms of this. So you just specify what you want and it'll generate the parameters for that.
I could totally imagine in a system like this, because you want to keep each code piece relatively small, there might be like cascading things happening. So like I call this, that creates a bunch of coins and then like calls the death predicate on these 5. And then we already see this sort of happening in Ethereum. If you touch one thing, it does a bunch of
calls to
other contracts. And then at the end of everything, you've dirtied like 15 places in the tree. So yeah, that's cool. Then you can sort of do a bunch of stuff in one mega proof.
Yeah.
This has some caveats though. So the issue is that doing this now, you're paying for. So in terms of privacy, you can either have like multiple parameters for 2 in, 2 out, 3 in, 3 out, or whatever combination you want. But the point is now these transactions will look different to observers on the blockchain. So the issue with this is that, for example, if I know that one particular contract can only be executed as 3 in, 3 out, then I know that, if I see a 3 in, 3 out transaction, it's probably for that contract. So then you lose some of your function privacy guarantees. And also from a efficiency perspective now, so let's say you don't want to have this sort of loss in privacy. What you can then say is everybody in the chain must use, say, 5 in, 5 out. But now everybody in the chain has to pay for this cost of 5 in, 5 out transactions, which is higher than 2 in, 2 out transactions. So you use like a efficiency, functionality, privacy trade-off that you have to make. So what you can generically do is sort of stripe your computation across transactions. So you can be like, okay, I'll conduct part of my transaction, my computation in this transaction, and this leaves some intermediate state. I'll use that intermediate state for computation, and I'll put in a new transaction, and then so on and so forth. So you keep propagating your state and keep dividing your computation up across transactions. And that's also possible, but that again makes reasoning about this stuff trickier.
Just to go back for a second on that, when you talked about the different numbers of coins that you could actually have, is that something that would be consistent throughout an implementation, or could that be different per ZK snark?
Within the same system, you could have like different transaction types, which say 2 in, 2 out, 3 in, 5 out, whatever number you want. And that's entirely possible within the same system. You would have to have different snark parameters. So basically in the end, for this mega proof that we talked about, it has to verify either 2 in, 4 proofs or 10 proofs or whatever. So for each of these different numbers, you would have to have different parameters. So that makes some of the cost a bit trickier, but you could use something like Sonic, for example, which has this nice property that your setup is entirely universal, right? So you can use something like Sonic to get around this problem of doing setups per number of inputs, outputs.
Wouldn't you have to do a setup per contract that you deploy as well?
Yeah, so that's one big downside that we are hoping to address in Zexe. So as I said, so now we have a proof per predicate that is executed in the transaction, right? And as we know, snarks have this terrible problem of trusted setup, or at least the most efficient snarks have this problem of trusted setup, right? There is a per application setup. One nice thing in Zexe is that we're able to isolate these sorts of different applications so that if one application does some malicious setup, as long as they don't use that application, it can't affect me in any way. Only the users of that application will have to suffer the consequences of this, malicious trusted setup. But that still leaves the problem of the applications that I do want to use. How do I trust that their setup has been done correctly? So this is where, one nice feature of our implementation is that it's entirely, and our construction paper is that it's entirely generic in terms of proof system. So we use a concrete proof system in our implementation that requires a particular per application setup. different one. But we can easily replace this with something like Sonic, which has a universal setup. So you do this universal setup, and then each application can deterministically derive their SRS or their public parameters. So you only need to trust this universal common reference string that everybody in the world has to use. So as long as everybody trusts that, then your application is also secure. And so there's a lot of work coming up that tries to build on Sonic and improve efficiency there. So we could deploy that in Zexe.
This is really cool because this is like we had Sean Bo on talking about Sonics, and this is like kind of a place where we see. I mean, I think we've heard a few things today at ZCon where Sonics can really come in and help, or this universal trusted setup could be incredibly helpful to solve a lot of the problems that concepts in
and not
space
necessarily just across all like predicates in Zexe, but across multiple blockchains even.
Yeah, you could just have one setup across
one universal trusted setup in the world.
And that just increases the trust across all of these systems because now everybody has to trust it.
Yeah, it's pretty cool. One thing I'm curious about with the construction is, you have this UTXO model. Have you thought about applying it to an accounts-based model, something like Ethereum? What's the pros and cons with that?
So we did think about this, and I think that it might, I don't know, maybe I'm just being very negative and cautious. I'm not sure how one would achieve the same sort of privacy guarantees that you can achieve in the UTXO model that you would in an account-based model. Mostly because, so the issue is that, so now let's say I have a smart contract in Ethereum, right? Somebody invokes this, and now the state gets updated. Yeah, so concretely, let's say, I don't know, it's some sort of token smart contract, right? So somebody makes a payment to somebody else. So this involves updating some locations in the table of this, in the database of this smart contract, right? The problem with this is now, how do you hide which locations are updated? In the UTXO model, this is okay because in some sense, this table is distributed across the entire blockchain in some sense. But in this account-based model, if you want to hide which location is changed, which balances is decremented and which is incremented, that would require somehow touching all the other locations as well, right? Because you can't reveal which location was touched. And this is really the problem, like extrapolating this to like generic computation. This is a problem with getting this sort of privacy in account-based models. So there's some work, like I think it's called Solidus. It's from IC3 folks, which does this in a very, very permission setting where there's maybe like 3 or 4 nodes in your ledger or something. They do it in like between banks or something, where there's a specific cryptographic primitive called oblivious RAM, which allows you to do this sort of oblivious this update to one location without revealing which location is updated. So there is a way to do this, but it's not really scalable if you have thousands of people updating the database at the same time, from what I understand. Taking this sort of strong privacy guarantee and trying to put it in an account-based model, at least it might be beyond the reach of our current techniques.
So let's get back to the proof systems. You said it was generic over any proof system.
Mm-hmm.
Which ones have you implemented? Which are you planning on using? Like what fits? What's a good proof system to use with this?
Okay, so to clarify a bit on the generic proof system, we do require some conditions on the proof system. So at least for the predicate proofs, so for the per application proofs, we need them to be succinctly verifiable. So what I mean is existing snarks like, I don't know, Groth 16 or Groth Malus 17. What these provide is the ability that when you verify the proof, it's constant time, independent of the size of the computation that occurred. So the nice thing is that the proof is short, but also verification time is short. Something like bullet proofs, you get the property that the proof is short, but verifying it still takes as much time as proving, right? And this doesn't quite work, at least in our design of the system, mainly for the privacy guarantees.
All right, because it's sort of a timing attack thing, where if you can determine how long some contract takes to execute, you can see which contract they call by measuring the verification time.
Yeah, exactly. If you know that the contract is supposed to take, one contract takes 5 hours, one contract takes 10 hours, you can see, this verification is obviously faster than the other one, and you can exactly tell which contract is being executed. So you lose your function privacy guarantee. This function privacy is really a big reason for a lot of the decisions that we made. But yeah, so because of this constraint, we want this succinct verification. We've mostly been limited to mostly these pairing-based snarks, ZK snarks. In particular, in our implementation, we implement this Groth-Mahler 17 because this also provides this technical property of so-called simulation extractability. It basically prevents, in some sense, replay attacks within the blockchain. So that's the one that we use. It's pretty efficient. Proof size is very tiny. It's, I don't know, less than 200 bytes. Verification is also only a few pairing equations. So it's very nice. The downside, of course, is this per application setup that you have to perform. The nice thing is that we can, our system being generic, we can replace each of these with something that is still has the same succinct verification and succinct proof size property, and replace that with something that doesn't have this universal setup drawback. So maybe in the future, if it happens, you get some sort of, I don't know, something like Sonic is improved that it so that proving and verification all are very nice and fast. Then we could drop that into Zexe with, I mean, they would require some changes, not to the core infrastructure, but just maybe writing constraints to verify proofs and stuff. So there'll be some work, not a large amount of work. You could drop those in. In the future, maybe if you get some sort of very efficiently verifiable Starks or these IP-based snarks that Alessandro was talking about also at ZCon today, then you could also drop those in. You would have, at the moment, the downside is the proof size is a bit larger and verification time is a bit worse. So, but it's plausible that they can bring that down as well. And then you could just drop those into Zexe as well. So it's very generic. The requirements are, it should be zero knowledge, succinct verification, and succinct proof size. And that's the, I mean, they're not non-trivial demands, but there's a number of constructions which meet them. And which probably there'll be more in the future.
Getting a chance to be here at ZCon and around a lot of really good cryptographers and academics, researchers, I actually asked some people who had read the Zexe paper what they wanted to ask you. And one of the questions was, could efficiency be achieved by sacrificing generality in the death and birth predicate?
So it does depend on the application. So if you want to specialize, say, Zexe and say, okay, I don't care about doing general computation. I just care about, I don't know, tokens plus maybe a little bit of, I just want to do dexes, for example, or some atomic swap. Then, yeah, you could hard code all of that information into, say, your one parameters, and you don't have per application parameters, and then that's it. Yeah, then you get actually probably a 10x boost in efficiency. So you get a massive improvement. It depends on like how much generality you're willing to lose. If you say, okay, I only want to execute these 5 computations, then again, maybe you can get slightly better efficiency than what we have. We don't know at all about what applications somebody might want to execute. So basically Zexe has to be ready for any application, right? That might come now or in the future, or people have not even thought of.
At this extreme end of specialization, doesn't it just become Zcash? Yeah,
you could just remove all the very fancy stuff and just be like, okay, I just want to do one payment with one sort of token, and then you have something like Zcash, probably less efficient because Sean and Era and everybody else has put in a lot of effort into optimizing it. But yeah, you would have that. And you could go like a couple of steps. You say, okay, I want multiple tokens, and then okay, then that's something that you can do. Then you can go a couple of more steps, and then be like, okay, I want to do a little bit of maybe very simple Bitcoin scripting kind of thing. Then maybe you get, I don't know, then you're already at like some level of generality where you don't really buy much from not being fully general. Like you're still paying a cost, but you're not getting full generality. So at that point, you might as well be like, okay, I'm going to support arbitrary computations. There's a big gap, I think, between supporting some very minimal set of computations, and then once you start bleeding over into in very, very limited sort of generality, then you pay the full cost anyway, so it doesn't make sense to not be fully general.
In the case, so we didn't actually get a chance to touch on this, but one of the use cases that you will often talk about in presentations, and actually it's in the paper as well, is it's like a private scaled DEX in a way. In the case of that example, how generalized is it?
So you could limit, so you can, we have this progression, right? You go from Zcash to you add one more token, a couple more tokens, and you have multiple tokens doing the same thing. That's still very far from generality. So you can do that with a few tweaks to the Zcash protocol, for example. So you have that, and then if all you wanted to support was just this DEX sort of application, you could also do that without sacrifice or conceding much in terms of generality. You just have this very simple, I don't know, you check that the other coin is of what you want to exchange it for. And then again, you're not anywhere near generality. So now they're still limited at like basically 3 things, right? Now you can trade, and then you can trade between assets, and that's all you can do. The moment you want to start doing more general stuff, like you want to have any sort of user control on what is being executed, then that's where you need the generality. So if you're just limited to just dexes by themselves, and that's all you care about in the entire lifetime of your system, then there's but there's less need for a lot of the infrastructure that we develop in Zexe. But if you want to have any sort of user control on what they want to execute, then that's where you want more of the generic infrastructure.
Cool. The other use case that you have is a private stablecoin.
Yeah, so that case is a bit more interesting because what we support or what we discuss in the paper is some sort of, not just stablecoins, but any kind of token where you want to maybe perhaps change the policy surrounding, issuance of the coins, or blacklisting or whitelisting of addresses. And in these cases, you actually do want to update the policy as time goes on. And there, having some sort of generic infrastructure is actually very useful because the policy changes. So now you need to support different policies, which is, you don't know what the policy is going to be. So you have to be general.
One other question who came from one of the co-authors of the paper, Howard Wu, he was talking to me. It wasn't exactly a question, but he was talking to me about all these other things that would be amazing to include. So if you had a wish, what would you like to include? What would you like to have included in this iteration of the paper?
So I don't know what Howard was talking about. Both of us were super tired at the end of working on Zexe because we started it basically. So in the beginning of the talk, I said how this decentralized micropayments paper was sort of the inspiration. So that paper was published sometime in 2017, and we started having the seed ideas for Zexe a couple of months after that. So this is we started working on the very, rough idea of Zexe in maybe June 2017. So, and we published the paper we put on ePrint in October 2018 or so. So, which is a long time to work on that. So, this is me and Howard, and Sean. We worked on the implementation, and implementation was difficult, but also formalizing all these ideas of how do you program and what sort of security guarantees and privacy guarantees you get. So, all that was worked out with Alessandro and Matt and Ian and everybody else. So, just all this entire process took very long. So, already the paper is very dense in both conceptually as well as in terms of the implementation side of it. So I don't think that any reader would have, by the time they get to the end of the paper, would have. They'd be too tired to absorb more concepts.
Who knows? Maybe at then they're like, give me more.
And that's a 75-page paper, so you have to be very, very excited, enthusiastic reader. In which case, they can just talk to me or anybody on the paper.
So you mentioned a bunch of other people there. This is obviously shared work with a lot of people. Who is involved? I'm also super curious to hear what is actually implemented, what exists in theory, your implementation, what is it written in, where can I find code?
Okay, a lot of questions. Well, let's start from the beginning. So, so this is joint work with a lot of brilliant people. Alessandro Chiesa is my advisor at UC Berkeley, Matt Green and Ian Mears, who were at JHU. Ian is now faculty at University of Maryland. So congratulations on that. Sean Bowe, who was on the podcast previously, but he is one of the foundational aspects for writing a lot of the code. And Howard Wu is also, me and him collaborated on a lot of the code. So it was very much a group effort, both on the conceptual side and the implementation side. And it really needed, I think, everybody's inputs to formalize what we wanted and actually get some sort of reasonable system at the end of it.
And to the second part of Frederick's question, what has been implemented and what is sort of in the pipeline to be implemented? Yeah,
so the implementation is basically we have implementation of the transaction creation mechanism, the transaction verification mechanism, and the setup mechanism. All that stuff is implemented. What we don't have is, we haven't hooked it up to some sort of blockchain that you could plug in. So we've written our code in a generic enough fashion that you could take it and plug in something like the Cosmos SDK or the Parity Substrate SDK, and you can just anything which has some sort of blockchain mechanism, you give it a bunch of transactions and it implements the chaining and block creation mechanism for you. So as long as you have that, you can take our code and plug it in. Everything So you can, with our code, you can create the transaction, verify it, all that stuff works. You just need this database or blockchain underneath to plug it into. It's implemented in Rust. But yeah, we have like a implementation of the finite field arithmetic, the snark stuff, gadgets for these snarks and constraint systems, and then Zexe, like this transaction creation, all that stuff on top of that. And yeah, a large fraction of the code was like built on top of what Sean and Dara worked on, namely the pairing and Bellman libraries, as well as a lot of techniques from the sapling version of Zcash for like the efficient Pedersen hashes and all this stuff. Is like a core component of Zexe as well.
Where can I find the code?
Yeah, so the code is at libzexe.org, so libzexe.org. And the paper is also online. If you just I don't think Zexe is a very common word to search for. So if you search Zexe, you'll get a bunch of links.
I've tried it. I think it's a little further down, but maybe it'll move up in SEO.
Maybe on my computer, Google has learned what I do. So it's the first result.
Cool. Well, thank you so much for being on the podcast and telling us all about this very, very interesting concept protocol paper. Good luck with it.
No, thank you. Thank you very much. It's all my pleasure to be here. And yeah, it's a fantastic platform.
Thank you. And to our listeners, thanks for listening.
Thanks for listening.